Hello, everyone, and thank you, Liam, for the introduction and for the invitation to speak to you all today. As Liam mentioned, my name is James Paynter. I'm a fourth year PhD student at the University of Melbourne. And today I'll be talking to you about some research I did with my PhD supervisor, Rachel Webster, and another collaborator, Eric Thrain. And as you may have read from this title slide, it's evidence for an intermediate mass black hole through a gravitationally lensed gamma ray burst that we discovered. And the background here is an artist's impression of that done by the artist at Swinburne, Carl Knox. And so this image here is the black hole in the center, and then the two sight lines of the gamma ray burst. And so we're looking sort of down the barrel, and I'll speak more about exactly how this image works in a few slides. So a bit more about me. I'm a COVID refugee. I got sick of lockdowns in Melbourne. You might have heard we were one of the most locked down cities in the world. And so I made my merry way up to Queensland in the Sunshine State. And I'm currently on Moreton Islands, which you see here, which a fun piece of trivia for you was where they filmed the 2002 Scooby-Doo movie, which is just a couple of kilometers to my left. Oh yes, and so I may soon be on the hunt for a postdoctoral position to anyone with funding who may be listening. Okay, so just a brief outline of the talk today. First, I'm going to introduce gamma ray bursts, GRBs, and then speak about the gravitational lensing aspect. Then I'll dive into some data, so the data set that I was looking at, and then talk about our discovery. And then luckily for us, we published our results first, and then there was a string of GRB detections after that. So I'll talk a bit about the other detections as well, and speak about them together. And then discuss where the intermediate mass black hole gravitational lenses that we've discovered may be hiding, because as you may know, intermediate mass black holes have sort of eluded astrophysicists and astronomers for a long time. So now that we've detected such a large number density of these objects, the onus is on us to suggest perhaps where they might have come from. And then to finish off, I'll place our result in the context of intermediate mass black hole and supermassive black hole formation. Okay, so gamma ray bursts. We either have a large star undergoing a core collapse supernova at the end of its life, or during the merger of two neutron stars. In either case, the remnant is a black hole, and rapid accretion of the matter that surrounded either the merger or the collapsar star will accrete back onto the black hole, form an accretion disk, and shoot these two bipolar jets along the rotation axis. And the Lorentz factors here are of order 100, if not more. And so because we're looking at down the line of sight, so if you look down the line of sight, you see the gamma ray burst. If you're off the line of sight, so you have to be looking down here to see it. If you're off here, you miss it because of the Doppler beaming is so great. So this is our Lorentz invariant, and that results in not only the number of photons being increased, but also the energy of these photons is greatly increased too by that Doppler beaming. So what does this look like at the detector? On the left is a typical gamma ray burst pulse. It's the fast rise exponential decay shape. And many of the gamma ray bursts, I think it's about 80%, have this shape. And then on the right is a more structured burst. But you can see that each of these individual pulses, although it's a bit compressed in time, still has that same fast rise exponential decay shape. And you can see that it's peaking in sort of the 100 to 300 kilo electron volt range. And so before I started my research, there was no candidates in the literature really of gamma ray burst lenses, but we know from quasars, which are another cosmological object, that they experience strong gravitational lensing, which is formation of multiple images at about 0.1 or 0.2%. So with 10,000 gamma ray bursts, you would expect there to be some lenses in that data set that were so far undiscovered. Now, quasars experience reddening and dust extinction by the material along the lines of sight, whereas more or less the universe is transparent in the 100 kilo electron volt gamma ray energy range, which gamma ray bursts peak. So we expect that there's nothing really along the sight lines that is going to distort the two images such that we can't say that they were a pair. Furthermore, due to the angular resolution of visible telescopes, optical telescopes, the sensitivity of mass ranges, which quasars are sensitive to, is greater than about 10 to the 11 solar masses. Whereas for gamma ray bursts, we're sensitive to a much larger, broader range of masses, from about 100 solar masses up to that same 10 to the 11, 10 to the 12, 10 to the 13 that quasars are. So this is a diagram of the lensing schematic. We've got the source, the distant source, and then this gravitational lens in the middle. And the gravitational field, if it's strong enough, is able to distort the light emitted by the source, such that there are two paths created to the observer here on Earth. And if this lens can be described as a point mass, that is, if all the mass is internal to these two lines of sight, and we can describe it as a point mass, then we get this wonderfully simple equation relating the redshift of the lens, the mass of the lens, to a few constants that we're all very familiar with from perhaps even high school physics, to this observable the time delay. So that's how long does it take for this image to get to us compared to this image. This one goes closer to the deeper into the gravitational potential well, experiences a stronger gravitational time dilation, and therefore actually arrives second, whereas the one that travels a larger geometric distance arrives first. And that is typically the brighter of the two images as well. And it is always the brighter of the two images in this simple point lens case. So we have our first observable, the time delay, and then the magnification ratio, which is just the ratio of the fluxes between the two images. And so then we have this more complex function here. But again, we only have two things that we observe, and we can immediately get out the mass to within a factor of the redshift, which is pretty good, I think. And so putting it all together, this is a short diagram I made when I was procrastinating my master's thesis. We have a core collapsed supernova turn into a black hole. It shoots off these jets, which then in turn launch the gamma rays. There's some mystery lens here, which distorts the sight lines to create two of them. And here they converge again on the Earth and arrive now at our BATSI satellite. Okay, and we would expect that to look something like this, right? So we have that fast rise, exponential decay, pulse shape, which I spoke about earlier. And now we have two sight lines, so we create the two images, and we will then see those two images in time rather than a spatial image like the quasar quads. And that's because the detector sensitivity of these gamma ray satellites is quite low. For BATSI, there was an angular resolution of about 4 degrees. So you pretty much have Buckley's chance of resolving those two images. But because the time sensitivity is much greater, and BATSI had a clock cycle of 2 microseconds, so that's pretty good. And we can resolve these two images in time because they are transients, because they are short transients. Whereas if you had two overlapping quasar images, because they're persistent and because you're integrating in your optical, it's very difficult, if not impossible, to resolve them in time. Okay, so how would we want to detect something like this, these two pulses? Well, initially we could do an autocorrelation, and so that will look something like this black line here. And then we fit a polynomial to that, which is pretty arbitrary, but we fit this dotted line. And then we say, if there's any point where there's a correlation stronger than we expect just from this fitted line, so if there's any peak, perhaps when these two pulses are overlapping each other, then we say, all right, well, this is worth further investigation. Okay, and we expect from the equivalence principle that if we have these 4 energy channels, or as many energy channels as you like in other data sets, then we would expect that each of the magnification ratios would be the same, and that each the time delays between the two images will be the same too. And we're assuming the point lens and a point source, which for gamma ray bursts and black holes or other compact masses is a pretty good approximation. Okay, so I showed you what we expect our data to look like. This is our best candidate, GRB 950830. So we have two identical pulses separated by about 400 milliseconds in time. And if we do the autocorrelation function, we have that same dotted line, and then we have this peak at 390 milliseconds. And we can do it again for each of the 4 energy channels, and we find that the peaks are pretty much at the same time. So keep in mind that these are 5 millisecond bins. And these sigmas are referring to how far that autocorrelation function is jumping above the fit that we have there. So we found two pulses that are extremely similar, autocorrelating quite well. And I got to this point sort of by 2019, and I gave a presentation at University of Queensland at a Australian astrophysics conference. And then our second collaborator, Eric Thrain, spoke to me after the talk and said, look, you know, the work you've done is really great, but I think we can make it much more statistically rigorous. And so in the next year or two after that, I'm working quite closely with him, and we adapted the software that they use for gravitational wave modeling, and we use that for template fitting, and we use that for this. So first thing we need is a pulse model. So this is just the mathematical description of that fast rise exponential decay profile. We have the amplitude, this exponential, and asymmetry parameter psi. So that takes you from a symmetrical pulse and then perhaps pulls you this way or this way. So it makes your rise faster and your decay slower. And this, so the delta here is just an offset. When am I starting in time? And then tau is what is, how long is this pulse going for? So we can describe these pulses, although it's unclear exactly why they have this shape, or perhaps there's a few theories, but to me, it's unclear exactly why they have this shape, but we can describe the pulses pretty well with these 4 parameters. And so we can do a Bayesian model selection. In the no lens case, we fit 2 pulses, and that's that. So we have I1 with A1, Psi1, Tau1, Delta1, and then we have I2 with A2 and so forth. Whereas with the lens model, where we're saying, no, this is not 2 separate pulses, this is 2 identical pulses, then we're expecting that the second pulse here to be the first pulse shifted in time by some delta t, which is that observable that I spoke about earlier, and also scaled by the magnification ratio r. So we can observe both these things, or we can get both of these measurements from our data if it is a gravitational lens. Okay, so this is the software Bilby, and here it is converging on the solution. And you can see that we just fit a flat background. We've got the horizontal shift, the amplitude, the duration, and the asymmetry. And you can see here that there's this persistent residual structure. Now, for a lot of bursts, this isn't the case, that it does fit quite well, but we do also try and fit this structure, and we fit it with a sine Gaussian for the pulses that require it. Okay, so you can see a fit, and I'm not sure how many fits here. It is perhaps 100 shown. So it's quite well constrained what our best fit is. Okay, so we can do that to a few different pulses, and as I said, some of these are fit much better by the fast rise exponential decay, and some of them we get this persistent residual structure. All right, so here's some candidates that you would think look good as a gravitational lens candidate for a gamma ray burst, just based on what I told you. We can do the autocorrelation function, and they peak quite well, both of these candidates. And we can do this pulse fitting now. And on here, you can see 2 independent pulse fits. I think this is just with the simplest fast rise exponential decay model. And we can see that the residual structure is pretty good here, right? It's well fit. But over here, when we're forcing these two pulses to have the same shape, we find that now we've got quite a lot of residual structure. And so that tells you that the pulse fit isn't that good, right? And that's because you're forcing them to be identical. And this is described, well, this difference is described by the Bayes factor, which is just integrating over all parameter space over your prize and saying how well is the fit, you know, how much can I change my parameters before the fit isn't good. And if you sort of have a bit of space where you can do a lot of fitting, then you get a higher evidence. And so in this case, we find that the two pulse model is really much preferred over the lens model. And furthermore, I previously said that we expect the time delay and magnification ratio to be overlapping, if not identical, or we do expect them to be identical. Whereas our best fits, now you can see, and these energy channels, this is lowest energy, mid energy, 100 to 300, and then highest energy. And you can see there's a pretty clear correlation between what would be the magnification ratio and the time delay. And so we interpret that to mean, I just got a chat to say they can't hear me. I assume that's been fixed, that I can be heard, right?
I can hear you right now, yeah.
Okay, so that's been fine the whole talk?
Yeah, I believe so. Is that not true for everyone else?
I think it was right before. It must have been right before I started. Sorry, I only just saw that message. Anyway, so we have this clear correlation between the time delay and the magnification ratio. And we in addition to the Bayes factors, we can clearly throw out this candidate, right? Because that's not what we expect from gravitational lensing. Okay, now we do the same thing again with the candidate I showed you first, GRB 950830. We can see that the two pulses here, there's still a bit going on in the residuals, but I think it's mostly just noise. There's a bit of structure here, but in general, our pulse model, our lens model is now preferred over the two pulse model, right? And we fit a few different parameterizations. So we have the fasterized exponential decay, fasterized exponential decay with the residual fit as well. And all these different permutations that we try, the lens model is preferred. So we take this as a clear indicator that the two pulses are statistically identical. And then given what we know about gravitational lensing and given what we expect from gamma ray burst pulses, and that is that they do evolve over time, they do become less energetic, they do start peaking later. So there's a correlation between that peak in these different energy bins, which is sort of shown in this previous slide. So we do find that ours it fits what we expect from gravitational lensing, and it doesn't fit that expectation from gamma ray bursts of the pulses evolving in time. And if we look at the posteriors again on the magnification ratio and the time delay, we see they are all overlapping. And then so we can take all these samples for the time delay and the magnification ratio, we can run them through this equation that we had at the start, and now we get out our 1 plus redshift multiplied by the mass. And we do that, and then we find, hey, hang on a minute, this is peaking at a few times 10 to the 4 solar masses. And you know, that's pretty exciting because there's not many objects that are a few times 10 to the 4 solar masses, and especially not many that are compact. Okay, so about 5.5 times 10 to the 4, but that's also with the factor of redshift. So if we assume you know, a redshift of about 1 and a source redshift of about 2, which is reasonable given that we actually can't say that much about the data, since this burst was from 1995, there's no follow-up that can be done. So that putting a redshift of about half or 1 brings this down even further to about 30,000 solar masses. Okay, so it could possibly be a globular cluster. However, I did order of magnitude calculation, just estimating how many globular clusters are attached per galaxy, and looking over all galaxies. And I found that, well, the density of these lenses is about 5 times 10 to the negative 6. And I'm not sure if I mentioned before, but our optical depth to lensing, I think this must be in an upcoming slide, optical depth to lensing, so how probable that lensing is pretty much directly proportional to this number. So what this is saying is we have the globular clusters, but there's not enough of them for us to expect to see a lens by a globular cluster. We would need about 100 more candidates before we expect to see a globular cluster doing the lensing. Now, there's also dark matter halos, so NFW profiles. We know that these are extremely numerous, and we know they make up a large fraction of the energy density of the universe. So perhaps it's one of these, or perhaps it's a long fabled intermediate mass black hole of which we don't know the number density. Okay, so this is the slide I was asking for before. Our average optical depth is our number of lens candidates divided by the total number of lens candidates. So that gives us our average. And then we're integrating that over source counts and redshifts. And then we're integrating this optical depth. Okay, and that's an integral over the volume that you're exploring, multiplied by the number of lenses within that volume, multiplied by the effective cross section. So how much how much leeway do you have before you get the 2 images versus getting no images at all. So multiply these things, 3 things together, we get the optical depth, which in turn gives us our probability of lensing. All right.
I have a favor. Someone is not muting themselves. It's hard to hear the speaker and the. Could everyone who's other than the speaker mute yourself?
I think it might actually be background noise, but I'm not sure.
How's that now?
Yeah, I mean, there's still some background chatter, but.
Oh. Well, I'll just speak louder. Is that going to work? All right. So in this graph, we have the integral that I described above for different redshifts, and this black line here, or red line now, is our probability of lensing. So that's cutting across here, and where this meets the integral above, we can drop down and say that's our lens density. Okay, and so here's the globular clusters down here at which we can rule out at 99.999% credibility based on this estimate here. Okay, and this again is just a determination of the lens density, assuming that mass of a few times 10 to the 4 solar masses, and that also under the assumption of a source redshift of 2. So these lines are for source redshift. So if you like, and you say, no, actually, I think your gamma ray burst is at 0.384 down here, then you infer a much larger density of lenses, and that is because you're exploring a much smaller region of space, and therefore you expect the number of lenses to be much smaller. Okay, so I already kind of said that we rule out globular clusters just based on the fact that there's not enough of them in the universe to form these lenses. However, it could be a dark matter halo, and we can see that this evolving with mass. So this is our lens density, and so we're looking right down on the left here. We've got a few times 10 to the negative 3. However, these smaller dark matter halos are much poorer gravitational lenses because they're too diffuse to create the multiple images. So they're not compact enough to form good gravitational lenses effectively. So it is possible that it could be a substructure in the halo. However, again, finding that substructure with the right quality and the right compactness brings down the probability much more. Okay, so from now on, I'll speak about under the assumption that it is lensed by a black hole, because we've arrived at a number density of these objects, an omega of a few times 10 to the negative 4. And therefore our space density, the number density of these objects is 2000 per megaparsec cube. Okay, and this is just a slide for the paper, which finally got published after a few years of work. So please check it out if you haven't, or if you want to know more about what I've spoken about today. Okay, and so as I mentioned right at the start, not long after we published, a new discovery was made, and that's GRB 2000 200716C. So not only do they have the two images here, but they also have spectra. And this was found by not one group, but two groups, and they inferred not identical, but very similar estimates for the lens mass. So they looked at the same GRB, same data, different authors, but they both came to the conclusion that it was lensed. And one of these groups, Yang et al., even were kind enough to use the software that I'd written, which is a very flattering thing indeed. Okay, and this is the software package here, which I published a couple of years ago. Okay, so they also had the spectra, and they were able to say not only was the two pulse shapes identical, but the spectra were identical as well within the statistical boundaries of their problem. Okay, and now again, I think this was mid last year, out of Iran and Oman, another gamma ray burst candidate, 090717A, and they're finding a lens mass of 3.6 times 10 to the 6. And then another one last year with a lens mass of about 10 to the 6 solar masses. And again, they have a spectrum here, which they find is concordant, and the two pulse profiles, which they find are concordant as well. Okay, and so that almost leads us to somewhat of a problem that we have too many gravitational lenses, although it's still possible, because I said at the start, we're expecting a few in every 10,000 bursts, and now we have 5, I think, and possibly more. So that inferred number density really shoots right up. So then we have to begin asking questions. Well, how much do we really believe certain candidates? How much, do we really believe these candidates exist? So two authors, Mukherjee and Nemiroff, have sort of come out several times to say, no, these gamma ray bursts are not convincing gravitational lenses. I mean, as you can read from the titles here. But another set of authors who published these two GRBs on the bottom said, well, actually, we found that the chi-squared test that these two authors have been using to say, no, that the lenses aren't similar, that's actually extremely sensitive to the bin sizes. So it's certainly open for debate with some of these candidates if they are indeed gravitationally lensed gamma ray bursts, or if they are just looking very similar. And so now you might think, oh, well, boy, I don't know if this is a candidate after all. I'll come back to these two slides, actually. I don't know if this is a candidate at all, but luckily, I got an email a few months later from Harish Vedantam, and who worked with Tony Redhead, who I assume that you know. And he said, hey, I really loved your paper, and we found something really similar. So he sent me this original paper, and what they find is these symmetric U-shaped light curves, which are very hard to reconcile with anything but gravitational lensing. And so there's been several follow-up papers on this phenomenon. So not only do they find this lensing, they also find that the mass of these objects is similar to the lenses that we found, and they found that the number density of these objects is similar to what we found. Okay, so in this case, there's these caustic patterns which are created by a binary, and this binary is the supermassive black hole in the center of the galaxy, and then a compact lens slightly offset from that. And you can see along these best fit trajectories, they are able to create the magnification patterns, which are observable in the data. And the achromaticity is following from what I said earlier, that we're expecting these from the equivalence principle, that all wavelengths of light are affected equally for a small enough source. Okay, so I'll just go back to now about gamma ray bursts. So we're expecting these to be statistically identical because they're two images of the same object. But if we consider now that gamma ray bursts are emitting at ultra high Lorentz factors, and perhaps it's possible that if the emission surfaces are not smooth like we are assuming or finding, and they are slight inhomogeneous in some way, then perhaps it's not reasonable to expect that both lines of sight will be looking at exactly the same image. There exists some angle that you can bend apart the two lines of sight. So there exists some lens mass, which is big enough that you're looking at now at two causally disconnected regions of the gamma ray burst emission surface. So then you would not necessarily expect them to be statistically identical anyway. And something that I haven't mentioned previously is that we actually haven't found any gamma ray bursts lensed by galaxies. And so the optical depth that we're finding is sensitive to the lens mass. The quasar optical depth to multiple imaging by galaxies is 0.1 to 0.2%. So we therefore expect that we should see not only lensing from the intermediate mass black holes, or millilensing from these 10 to the 4 solar mass objects, but we also expect there to be lensing from galaxies, and we haven't seen that. So it could be possible that these lines of sight, that they exist in the data, but actually we haven't been able to detect them because they are more different than we expected them to be.
Well, but the lensing on by galaxies like in quasars, those time delays are enormously long. So
yeah,
unless you're willing to go and look at, there's no guarantee that you would actually, even the detectors would be looking at the same thing a day later or a week later. So it's...
That's definitely true. That's definitely true.
Yeah.
But my impression now was that with Swift and Fermi and across the interplanetary network, that there would be coverage. Though you definitely raise a good point.
No, I don't think it's possible. It's just the numbers don't work out. This has been looked at a long time ago.
Okay. Perhaps we can speak more about that at the end. Okay, and I'll skip forward now. Actually, I think I'm running out of time. Okay, so if we consider now that this object is lensed by an intermediate mass black hole, and therefore our interpretation that there is intermediate mass black holes everywhere, we now have to understand, well, where do these black holes come from, and why can't we observe them through other means? And perhaps one of the main, if not the only ways we could find them is as a wandering black hole. Okay, so I gave this talk at Monash University in Australia, and I got a few questions regarding, well, if you've got 2000 per megaparsec cubed, are these getting jammed into galaxies, or are they getting spread in intergalactic space? If our Milky Way local group formed from a 20 megaparsec cube overdensity, then there should be something like 40,000 intermediate mass black holes in the neighborhood of our galaxy. So this is a image of our galaxy I found on Wikipedia. You can see here we are in the Andromeda. Do we stack them all in the galaxy, or do we sprinkle them around in intergalactic space? And if we put them in intergalactic space, actually, they're quite difficult to find, except through something like lensing. But then you also have to explain, well, how did they get there? Okay, so some of the observational consequences would be, if we assume that this mass spectrum goes as about mass to the -1 over 100 to 100,000 solar masses, then what we find is that we get roughly the same mass as the Milky Way. Furthermore, if they're in the Milky Way, we're going to find that they're going to relax and spiral down into the galactic core. With just 100 of these relaxing in 100 million years, the Sagittarius A star at just 6 million solar masses would double in mass. If we consider the gravitational influence, which goes roughly as gm/b squared, giving us about 0.01 parsec, then we're expecting tidal disruption events and also the disruption of star clusters by possibly shooting through them. We can also expect microlensing in the Large Magellanic Cloud. This optical depth here goes as 10 to the negative 6, but the event rate scales as the optical depth divided by the event duration. So the larger our masses, the less the event rate is, despite having the same optical depth. And none of these have been found in Ogle. Okay, so if the Milky Way is an average galaxy harboring these intermediate mass black holes, they probably don't live in close where we would see their destructive influence. Now, wandering black holes are large black holes physically offset from their halos, halo center. They can be ejected from galactic nuclei during mergers, resulting in a merger kick, a gravitational recoil kick, or they can be ejected during multi-body interactions. If one of these mergers occurs with a low mass ratio, what actually ends up happening is tidal stripping. So most of the outer material will be taken by the larger galaxy, and that will leave just the black hole and its dense nuclear cluster of stars in general in orbit of that galaxy for some time. Now, simulations by Michael Tremel and collaborators have found that within a Milky Way type galaxy, there are 5 plus or minus 3 of these black holes of about 1 million solar masses within 10 kiloparsecs, and around 12 within the virial radius. So the simulations are finding that there's actually a lot of black holes out there, and this needs to be reconciled with our understanding from observations that there's only one supermassive black hole per galaxy. So I think this is really interesting, and I only discovered this while researching for this talk. And what they find is that these black holes are scaling with the galaxy mass. So for smaller halos, there's only a few, and then for much larger galaxies or galaxy halos, we find that there are hundreds of these wandering black holes. Okay, so how can we detect these? Through the accretion of diffuse gas? No, that's going to be difficult. I've mentioned before, they'll carry with them their nuclear cluster of stars, so maybe we could detect them through that. We can detect them through gravitational lensing. We can detect them through disrupting star clusters and tidal disruption events. Oops. Okay, so here's a paper that I found looking at hunting for wandering mass black holes through their accretion of gas in the low density into circumgalactic medium. But what they found is that they were detectable in the Milky Way, but only down to 10 to the 5 solar masses, and it's still very difficult. You have to actually find these objects and point your telescopes where they are. So if there's only 5 of them out there or 10 of them out there, there is difficulty in detecting them. Okay, a recent study by Jenny Green and her collaborators searched for wandering black holes by the cluster of stars that were attached to them. So they searched for small clusters of stars of a few thousand, and their modeling predicted that there would be about 100 intermediate mass black holes from 1,000 to 1 million solar masses, but they found no candidates in the Milky Way. And their limiting assumptions are stated on the right, that that all these stars would be main sequence stars, that the cluster is dissolving if the mass is under 10 to the 6 solar masses, and they're assuming a radius of 1 parsec. Okay, so if we look at this image here, it's from M60. We can see the main galaxy here, and then a neighbor, and then there's this ultra compact dwarf down the bottom here, and this dwarf harbors a 20 million solar mass black hole, which makes up 14% of that dwarf's mass. Okay, so that that is likely a tidally stripped galactic nucleus. Then another recent discovery of, and as you might notice, 20 million solar masses is not exactly intermediate. So if we look at a little closer to home now at Andromeda, a recent discovery by Piketty and collaborators have found this 100,000 solar mass black hole. So the mass of the cluster is about 6 million solar masses, and then the black hole is making up 1.5% of that dwarf. So the question we have to ask ourselves is, well, do we really expect that these black holes are going to be by themselves, or will they be carrying a cluster of stars with them in the outskirts of a galaxy, having had most of their material stripped by the main galaxy? This is just a simulation of that, but I'm running out of time, so I'll keep moving forward. So this is looking at Ogle data Gaia data, looking towards the Large Magellanic Cloud by Lukas Wyzikowski and Ilya Mandel, and they find microlensing by dark objects from 2 to 10 solar masses. So they're not intermediate mass black holes, but they are getting up into that larger range of masses. Okay, so that these objects, dark objects, are there, and we are finding evidence for them. Okay, this is some older work now looking at VLBI jets, which says that if dark matter is mostly a million solar mass black holes, then when looking at VLBI jets, we would expect these distortions that is due to gravitational lensing from the point masses, a million solar mass black holes. However, and this is from 1994, but there was no evidence for that found. So there was early constraints on the number density of these objects. However, at 10% of the dark matter mass density of 0.3, it's still quite a large constraint, a large amount of parameter space available. Okay, tidal disruption events, the duration of that correlates well with the mass of the black hole. And furthermore, white dwarfs being tidally disrupted are limited to a black hole of 100,000 solar masses. So if one of these is observed, that's a dead giveaway that there's 100,000 solar mass black holes or less mass that are out there. Okay, and then obviously LISA, once it comes online, will be sensitive to a large range of masses here, particularly sort of around 10 to the 6 solar mass merger product. Okay, so this is the sort of the black hole mass spectrum. From the lower end, we have LIGO being able to detect these objects. LIGO is sensitive to a merger product of up to 400 solar masses, and we know from, I think it was last year or the year before, the 150 solar mass discovery was coming into the lower end of intermediate mass black holes. Then from the higher end, we have these discoveries in dwarf galaxies, active dwarf galaxies, LISA, these wandering black holes which have been found in orbit of other larger galaxies. And then in the middle, we have possibly accretion, gravitational lensing, and tidal disruption events, allowing us to explore the full range of parameter space. And I'll just say that the number density, so say we get, say we had 100 lens candidates and we were therefore able to fill out the mass spectrum. And we can then fill out this graph here. We would then be able to help determine, well, where these black holes formed from gravitational runaway, which is black holes sinking to the center of the cluster and creating a large supermassive black hole seed, or were they created from population 3 stars, which are the earliest generation of stars, were hydrogen-rich, metal poor, able to create very large stars and therefore very large black holes of 100 solar mass as their remnants. Or were they formed from direct collapse, which predicts a number density that sharply declines at lower black hole masses. All right, so quickly summarize. We found evidence for a gravitationally lensed gamma ray burst, which we conclude was lensed by a intermediate mass black hole of 50,000, give or take, solar masses within that factor of redshift. From this, we inferred a number density of about 2,000 per megaparsec. Other authors are finding similar lens gamma ray burst candidates and indeed similar lensing candidates of other objects. Lensing is one of the few ways to constrain the number density of intermediate mass black holes and will therefore be important to determine these formation mechanisms of the supermassive black holes. Thank you.
Thank you, James. Feel free to raise your hand and then we can call on you for questions. Go ahead, Shri.
Well, I'll ask the obvious question. I'm sure it's on everyone's mind here working on FRPs. Why won't you see a similar event with FRPs?
Why would we, or why haven't we?
Why haven't we?
I can't. What's the number of FRBs?
There are 10 to the 4 FRBs per day, whereas there are less than 10 GRBs per day.
Yeah, but I mean, how many FRBs have actually been detected?
About 1,000, I don't know. I've not kept track. Maybe 1,000.
There's about
Okay.
700 public.
Okay, so in this case, then compared to the GRB catalog of 10,000, it's much smaller. I mean, the statistics should be the same, right?
Hang on. Oh, which GRB catalog is 10,000? The BATC.
I think all of them together. All of them together.
BATC is 2,000.
2,700. Fermi was about 3,000, I think.
And Swift had 1,000 some years ago.
Swift has a lot, but also now obviously there's overlap with Fermi, but it's definitely more than 5,000.
But anyway, there's a clear prediction here because the FRB rate is going to increase pretty fast. Unlike the GRB phenomena, which is pretty messy, it's got because you're really going over a very large range of energy. Here it's pretty straightforward. The bandwidths are small, and the effects are there's no frequency time dependence in at least on this sort of level. So this should be seen. And so let's see, you had, now have you gone through all the which is I was under the impression that you mainly looked at BATC and what else?
Yeah, I only looked at BATC. The other candidates from Fermi were other authors.
Okay, so let's call it about 5,000 or something, and you get 5 of them. It's 1 per 1,000. Okay, so in a couple of years, you have a prediction that.
Shri, I can actually help with this question because I've been computing these numbers recently, specifically for FRBs. The reason we wouldn't expect to have seen one yet is because of the redshift distribution of FRBs. The lensing optical depth goes like Z cubed out to redshift 1.5 or so. So if FRBs are 2 times nearby or 4 times nearby, then the optical depth is more than an order of magnitude smaller. So I suspect we'll need a collection of 10, maybe 50 or 100,000 FRBs before we see this.
So what is the mean redshift of FRBs now that you think we have of the current sample?
If you use the McCord relation for the CHIME FRB sample, the mean redshift is maybe 0.4.
I see. Whereas at least for the Megaparsec sample, the redshift was 1. And for Swift, it's larger.
Can I ask a related question, actually?
Yeah, sure.
So you choose the mean redshift of 2 for the BATC GRBs, right?
Yeah, that was based on there was only 7 BATC GRBs that had their redshift measured, and that was done by Swift, I believe. So it's really poorly trained, I think.
So if you considered only short GRBs, then the number would be smaller, like maybe 0.8 or something. And on short GRBs, those are the only sources where you could look for lensing by a mass of 10 to the 4 solar masses, right? Because it's like a couple hundred milliseconds.
Yeah.
So if you consider only short GRBs, then the implied omega IMBH is huge, like impossibly huge. So can you justify using the full set?
I mean, that's a good point. What's our time delay for? Yeah, and I think the short GRBs are actually the redshift distribution is a bit lower as well. So you're right, and no, I can't.
I'm puzzled that you're saying that we know the redshift distribution of BATC at all.
No, I don't say that we don't know the distribution. I said
no. I'm saying we even have any redshift for a BATC burst. I'm unaware of that.
I think there's 7 of them.
How's it possible?
Because they were simultaneously seen by Swift.
No way. BATC was dead before Swift went up.
Look, I can't remember. I did it 2 years ago, but I definitely found
the sort of the BATC is mainly unique for its sort of a higher energy, because these numbers depend on the mean energy of this GRB, as well as the duration, as Liam points out, which is extremely important point, because the mean redshift of the long duration GRBs is of course the one which is larger. I forget what it is now for the short one. Maybe it's 0.4 or half. I don't think it's even 1. So the best one for the long duration, if you use, is Bayesian, and that redshift is 1. Now, curiously, if you want to get high redshift, you have to go to the softer events. Mainly not because the redshift reddening or whatever it is, it's just that at lower energies you see more of the less collimated ones. And so Liam, your argument, I'm not sure is, would actually, I mean, it's a very good point, but once you get into this, the relevant sample, you may find that in fact, for these ones which are sharp and high energy, the redshift range may not be too different than what you're seeing with the FRBs.
Interesting. Tony, do you have a question?
Yes, I do. Thanks. Really just, James, I got the impression from your talk, and maybe I'm wrong about this, but that you felt that the more recent, the 4 or 5 more recent candidates were equally as good as your original. Is that true, or do you have any doubts about any of them?
I don't have doubts about specific ones. I think the fact that the new ones have spectra as well, because they're from 2009 to this year, so they have, or last year, sorry, so they have much better. They have Fermi and Swift, so they have spectra, which is aiding that detection, and because we're expecting the spectra to be the same as well. However, only a few of the authors, the way that they actually did the pulse comparisons, the light curve comparisons, I'm not necessarily convinced on all of them, and as well as the pulse fitting. If I just fly back here. So for this one here, for example, you can see that there's these two pulses here, and they fit a fairly simple model. So it's not, because I didn't do it, it's not clear to me exactly what was done, if that makes sense. I think, in general, yeah, they're good candidates, but definitely worth maybe even assigning a probability to how much you like each candidate, and then if you wanted to estimate the number density from there, you could weight it by your candidates. So I think they're good candidates, but I think definitely worth looking into further if one was to take them as a sample.
Okay, thanks very much. I also had a couple of comments. One was, I presume you must be aware of it, but Amy Reines and James Condon and Darling and Green have been finding, small, lower mass black holes in these dwarf galaxies, which they've been looking at. So that's quite a nice sample where they're finding lower mass black holes. And the other comment I wanted to make is that we did a study using VLBI, not of the distortions of jets, but looking for multiple images. So it's Peter Wilkinson and I had Caltech Jodrell Bank survey, and we looked at 300 objects where we had very, very good images at multiple frequencies in VLBI. So the papers, you may be aware of that, Wilkinson et al. 2001, but we put a limit of 1% of the closure density on smaller black holes, and then black holes that is less than 10 to the 9 solar masses. And we're now repeating that experiment with 20 times as many objects.
That's very interesting.
Carolina Casadio is leading this effort right now, but we should be able to push that limit down by a factor 20. So that'll be interesting to keep an eye on.
Yeah, I definitely would be interested to see the results of that work.
It's going to be a few years yet, but it's in the works.
Do we have one final question?
I don't see any.
Okay. In that case, thanks again, James. Thanks for joining us. It was a very cool talk. And see you all next week.
Thanks for having me.